Present here. I am Sangeeta Lakshmi, working as Assistant Professor in EC Department of R.M.K College of Engineering and Technology. Today we are going to see the session 6 of MOSFET amplifier, that is Unit 2. What are the topics we are going to discuss today is small signal analysis of common source amplifier with an unbypassed RS. Actually, in the last fifth session, we have discussed about the common source amplifier with the bypassed RS. Okay, that is a simplified analysis. So we are going to see the small signal analysis of common source MOSFET amplifier with unbypassed RS. Okay, so here first of all we have to know what is common source, right? Why it is called as common source MOSFET amplifier. Actually, the MOSFET having three terminals. One is gate, and then drain, as well as its three terminals. So this is your MOSFET. Here we have gate, here it is the drain, and this is your source terminal. The input, this Vi is the input, this may be an audio signal or your video signal, right? This signal will be given to the gate terminal, right? So the input is given at gate terminal, and output, this is your output. Output we are taken at where? Drain terminal. So output is taken at the drain terminal. So remaining terminal is what? Source, right? So the common terminal here is source. That's why it is called common source MOSFET amplifier. Okay, with unbypassed RS, that means here RS is present, right? First of all, we have to know what is the role of RS. The RS will provides the negative feedback. Okay, so due to this negative feedback, the gain will be reduces. Even though why we are using this RS means this RS will provide the good stability, that is the Q point. You know the DC load line, right? This is your DC load line. In x-axis we have VDS voltage. In y-axis we have the ID current, right? Always we have to keep the Q point near stable, that is center of the DC load line. Also it should be stable. Okay, so then only you will be getting faithful amplification. That's why we are using this RS. But the drawback is this will provide negative feedback. Due to that, the gain will be reduces. So to compensate that, only we have to connect the coupling, that is bypass capacitor, across this RS, right? But this analysis is unbypassed RS. That means you are not connecting bypass capacitor across this RS, right? So if you are connecting only with the RS, what is the impact created on this AV we are going to see. Our objective is, because of this RS, what happened in the AV? What is the difference between the previous analysis, that is bypassed RS, and this analysis unbypassed RS? We are going to see. Okay, and you know that what is R1 and R2? And R1 and R2 is nothing but the biasing resistors. These will provide the proper DC supply to the transistor, that is MOSFET, so that the MOSFET will operate in a saturation region. As you all know that if the MOSFET has to work as an amplifier, it should be operate in the saturation region. Okay, so that's why we are using this R1 and as well as R2 resistors. These two are called biasing resistors. Okay. Then we have seen what is RS, and RD is nothing but the load of amplifier. Okay, and what is the impact of the this coupling capacitor CC1 and CC2 means these two coupling capacitor will allow only AC signal. So this will block, that is, or it will isolate the DC signal. Okay, so that because of this coupling capacitor, the Q point will not affected because of the input signal. Okay, so the proper purpose of using this coupling capacitor is to isolate your AC signal from the DC. Clear? And what is this RL means? It is a load resistance. Maybe see here up to from here to here, it is the amplifier. Okay, from this point is load, and this point is input signal, that is audio or video signal. So the output of the amplifier is given to the load. It may be a speaker, right? This may be your speaker. So this output is given to the speaker. That speaker having some internal resistance that is represented by RL here. Okay. So next we are going to see what is small signal analysis. So far we discussed what is common source MOSFET amplifier and what are all the function of each and every component present in the common source amplifier we have seen. Next we are going to see small signal analysis. First of all, what is mean by small signal analysis? Small signal analysis is also called as AC analysis, right? See here, in the amplifier we have, this is DC supply, this is your AC, or it is called as small signal. Okay, why it is called as small signal means always the DC is on the order of volts, that is 10 volts or 15 volts like that. But in the input voltage of the amplifier, it is very weak signal, right? That signal is in the order of millivolts, for example 50 millivolts like that. So when compared to these two, in DC as well as this 50 millivolts, this is very small. No, that's why we are calling this analysis small signal analysis, because we are going to analyze the whole circuit only with this input signal VI, not with the DC, right? That's why it is called small signal analysis. Okay. So before going to analyze this, we have to draw the small signal equivalent circuit. Why means actually the objective of this analysis is we have to find out what is input resistance, what is output resistance, and what is your gain. Actually, for any person, if we want to analyze, we need to know his character, attitude, everything, right? Similarly, here also amplifier, if you want to analyze the characteristics, we have to know these three parameters. What is the input resistance? What is output resistance? What is voltage? Okay, for any voltage amplifier, the input resistance must be high. For any voltage amplifier, output resistance must be low. Always a gain we need always high. So whether we are achieving this high input resistance, low output resistance, and high gain, we are going to analyze this. Okay. So for that, first we have to draw the small signal equivalent circuit. How to draw this equivalent circuit? So first of all, we have to start with we have to set all the DC voltage to 0. This is your DC voltage, right? This DC voltage we have to make it to 0. That means ground. We have to connect it to ground terminal. Second thing is we have to short circuit all the capacitors. Why means already I have explained to you the reactance of the capacitance CC1 equal to, which is 1 by 2 pi FC1, right? So here, if the frequency is increases, the reactance will be reduces. The reactance reduces in the sense, ideally we can say XC1 is 0. Okay. Ideally we are saying, if it is 0 means it can be short circuited. It is short circuited. Suppose if XC is infinite means it is open circuit. You have to know this. Okay. So first of all, we have to draw the equivalent diagram now. So first step is, I told you, we have to make it to 0 voltage, all the DC voltage to 0. Second point is we have to short circuit all the capacitors. Then we have to draw the equivalent for this MOSFET first. So what is equivalent diagram means? You know that input is gate, output is drain, and common terminal is source. In between gate and source, we have the VGS voltage, right? VGS, that means the potential difference between gate and source. And in between drain and source, we have one current source that is called GM into VGS. Okay. So here we are not including the R0 because we are neglecting the yearly effect in the case of BJT, but here it is MOSFET. So it is called channel length modulation effect. We are neglecting our channel length modulation effect. So because of that, the R0 is infinite. Okay. So if you are neglecting channel length modulation effect, R0 will not include in your equivalent circuit because we consider that it is infinite. Okay. So this is your equivalent diagram for the MOSFET alone. Next, from the input side, we have this is also connected, this is also connected, and here also connected. Three resistance R1, R2, RS. Three resistance are connected to the gate terminal. Right. So from the gate terminal, one resistance is here R1, here it is R2, then here we have RS, right? RSI. So from the RSI, you have the here we have what? Voltage source connected to ground. Okay. This R1, this end is connected to gate, and this end is connected to where? This is connected to ground terminal. Right? Similarly, R2, one end is connected to gate and another terminal is connected to ground. So, R1, R2 as well as R1, both are connected to ground terminal here. So, we can connect these two to here because it is already ground. So, gate side is over. Next to source side, you can see this is your RS resistance, right? So, from the source, I have to connect one RS resistance. This RS resistance, another end here is connected to ground. So here it is connected to ground. Okay. So next from the drain, you have the RD resistance, right? RD is connected from the drain terminal. And RD, another end is also connected to ground. So from here it is connected to ground. And then this RL is also connected to the drain terminal. Because coupling capacitor we have shorted, no? So this RL also we have to connect it to the drain terminal. Clear now how to draw this equivalent diagram for the common source MOSFET amplifier? You can see the diagram. This is your equivalent diagram, small signal equivalent. I have explained you how to draw this, right? This is your diagram. I told you how to draw this, right? So in this, we are going to calculate first what is input resistance, what is output resistance, then we are going to see the AV. Okay. So first of all, if you want to see the input resistance looking into the amplifier, how to calculate? In previous slide, I have explained you. We have here the resistance, right? Here we have resistance, that is R1 parallel to R2 we have. This side we have the RSI and here we have the input voltage, right? So this is connected to ground. So when you are looking from here, what is the resistance? Ri. So when I am looking from here, I am having the resistance R1 parallel to R2, which is also called as Rg because gate resistance, right? Because the input is given at the gate, no? So instead of Ri, we can say Rg also. The next parameter is output resistance R0, which is nothing but the, we are looking the resistance back to the amplifier. So in this, if you want to find out the R0, we have to make Vi equal to 0. So this Vi, we have to make it to 0. If you are making this Vi 0, Vin also 0. Vin is nothing but the voltage across R1 parallel to R2 is nothing but the Vn. Okay. So that is 0 means definitely VGS, that is VGS is nothing but the, here we have the VGS, right? It is gate terminal. Here we have the source terminal. From the source we have RS, right? It is connected here. So VGS also 0. VGS is the voltage between gate and source. If VGS is 0, the GM into VGS, here we have drain terminal, right? It is GM into VGS. That is also 0. So if it is 0, this is open circuited. Here we have only two resistance. It is RL, it is RD. If I am looking from here, what is the resistance? RD is parallel to RL. So that will be coming in the output resistance. Clear everybody, right? So how to calculate R naught as well as R? Just you are looking from the input side of the amplifier, you can able to calculate the input resistance. If we are looking back to the amplifier, you can able to calculate the R naught, that is output resistance, which is RD parallel to RL. The next one is, see here, we have to find out the voltage gain. So what is voltage gain means? It is nothing but the V naught by Vi. So first of all, we have to find out what is V naught. Okay, so V naught is I naught into R naught. So I naught equal to what? Minus Gm into VGS. Okay, so next we have to find out what is Vn. Vn is nothing but the VGS plus Gm into VGS into Rs. So in that you have to take the VGS common outside. You will be getting 1 plus Gm into Rs multiplied with VGS. Our target is to find out the AV, V naught by Vi. But this V naught expression is only contains what? This expression, see here. This expression, this V naught, right? This V naught expression contains VGS. But I need what? Vi, right? So that's why I'm making V in equal to VGS plus Gm into VGS into Rs, so that I will get V in as in terms of VGS, right? Then we have to make VGS equal to V in by 1 plus Gm into Rs. You have to substitute in the first equation. You will be getting, see this diagram, it's clearly we can understand if you are seeing this diagram. Okay, so the what is the current flowing through here is I naught. Okay, so what is the voltage across here is V naught. So V naught equal to what? This resistance we had to combine together. So always as per the Ohm's law, voltage equal to current into resistance. So V naught equal to I naught into this RD parallel to RL. Okay, so RD parallel to RL. So this is nothing but the what? R naught, right? So that's why we have written here is V naught equal to I naught into R naught. We know that what is I naught, right? So I naught is nothing but the Gm into VGS. Here the current is coming this side, right? Gm into VGS, but the I naught is going this side. So it is opposite direction. That's why I naught equal to minus Gm into VGS. We have to substitute. This R naught is nothing but the RD parallel to RM. Okay. In this V naught is in terms of VGS, no. I have to replace by Vi. So how to make it is, first I am converting this VGS in terms of Vin, then I am going to write in terms of Vi. Okay. So for that, first I am making the relationship between Vin as well as VGS. See here, Vin is nothing but the voltage across R1 parallel to R2. So here also we have the voltages what? Vin, right? So this voltage is nothing but the sum of this voltage plus this voltage. So Vn equal to VGS plus the voltage across RS. The voltage across RS is what? The current flowing through the RS is nothing but the Gm into VGS. So here voltage across RS is nothing but the current Gm into VGS multiplied with this RS. Okay. So this is current into resistance, right? So the whole thing is nothing but the voltage across RS, right? So Vn equal to VGS plus voltage across RS. In that we have VGS common. I am taking VGS common outside. I will get 1 plus Gm into RS. Then I have to find out what is VGS because I have to remove the VGS from my V naught equation. So VGS equal to now what? In terms of Vin, that is I am making this term here itself. This alone will be going in the left hand side. I am getting this equation. Next I have to replace this Vin by Vi. So what is the relationship between Vin and Vi means? This is your input side. I have taken this input side, right? So when I'm looking from here, you know that resistance is Ri, right? When I'm looking from back side, I'm getting resistance is R0. So you just combine all the circuit into simplified circuit. So which contains only this Vi, this RSI and the input resistance R. That I have drawn here, right? So this Ri is nothing but you know that R1 parallel to R2. The voltage across R1 parallel to R2 is nothing but the Vin. Now you have to apply the voltage division rule, right? Voltage division rule. As per the voltage division rule, if you want to find out the voltage across a resistance, that is R1 parallel to R2 is the Vin. So I want to find out the voltage across that Ra, right? So Vn equal to total voltage Vi. This is your total voltage Vi multiplied with that particular resistance Ri divided by sum of these two resistance, right? So as per the voltage division rule, Vn equal to Vi into Ri by Rsi plus Ri. That I have to substitute in the second equation, right? I will get, see here, I'm getting that instead of this Vn, I have to substitute this Vi into Ri by Rsi plus Ri. Next, I have to substitute this equation 3 into, right? So if you are substituting third equation in 2 and 1, I will get final equation, that is V naught equal to what? I have to substitute equation 3 in 1. So that I will get V naught. V naught equal to minus Gm. This instead of this V just I have to substitute here now. So I am getting this expression. Okay. So what is the conclusion here is the final gain. If you are bringing this Vi in the left hand side, I will get the gain. Okay. So the gain equal to V naught by Vi, which is equivalent to minus Gm. This minus is indicated because of, I already told you, for the common source amplifier alone having 180-degree phase shift. That is indicated by this negative sign. Okay. So minus Gm into this Ri can be replaced by Rg by Rsi plus Rg. Okay. Into 1 plus this Gm into Rs, and in the numerator we have Rd parallel to R. Clear everybody? Right? So this is your gain equation for the common source MOSFET amplifier with unbypassed Rs. Clear pa? So in this you have to think this 1 plus Gm into Rs is in the denominator. This will reduces your gain when compared to previous common source with bypassed Rs. This gain will be reduces because of this parameter 1 plus Gm into Rs. Because this Rs will not appear in the previous analysis, but this analysis, this will be included. Because of this Rs only, the gain is reduces, right? So this is the analysis for common source amplifier with unbypassed Rs.